Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about conditional probability. The plan is to define conditional probability and then describe three very important results that are used all over the place in probabilistic modeling. Those are the chain rule, the law of total probability, and Bayes rule. Okay, let's start with a motivating example. Imagine that we want to model the probability that a flight is late if it rains. We're going to define two events of interest, L, which represents flight delayed, represents that the flight is late, and R, which represents that it rains. And from past data, like from past flight and weather data, we estimate the following probabilities. We're going to see how to estimate probabilities in the next video, but for now, let's accept that these probabilities are reasonable. The probability that a flight is late and it does not rain is 2/20. A probability that a flight is late and it rains is 3/20, so it's more likely. The probability that the flight is not late and it does not rain is 14/20. And the probability that the flight is not late and it rains is 1/20. Okay? All right, so now, just to refresh our memory, let's remember what the intuitive definition of probability was. Our intuitive definition of probability was that when we talk about the probability of the flight being late, we imagine that there's this experiment associated to our probability space where we can repeat it over and over and over and over. And each time we repeat it, we get one outcome. And that outcome tells us whether the flight is late and also whether it rains. Okay, we can see whether that outcome is in each of the events that we have defined. And then the probability of a certain event is how often the outcomes are actually in that event. So from all these repetitions that we perform, how many of them are in late. Okay, that's our intuitive definition of probability. Here we are not conditioning or anything, we're just remembering, like our intuitive understanding of what probability means. So now let's use our data to compute this probability, our data, like the probabilities that come from data or wherever they come from, to compute this probability of late for our example. So we realize that we can express the event L, maybe let me draw a small Venn diagram. This is L, and this is R. This is L, and this is R. Oops. This is weird because I have the shape drawing thing on L and R. Okay, so we express L as the union of all the outcomes that are in L and not in R, and the union with the intersection of L and R. These are two disjoint events, so we can sum their probabilities, and we know their probabilities from this information that is available. So now we can compute the probability of L as the sum of the probability of L intersection R complement and L intersection R. L intersection R complement is 2/20. L intersection R is 3/20. The probability that a flight is late is 1/4. This is not the probability we're interested in, okay? Like the whole point of this video is to define conditional probabilities. Okay, and that's what we're going to do now. But it was good to refresh what a probability actually is so that we see how to adapt the definition so that it becomes a conditional probability. And first, we're going to do that intuitively. So, intuitively, what should be the conditional probability of L given R, of a flight being late given that it rains? Before, if you remember, we were saying that, okay, we repeat this experiment many times, and we see how many times the flight is late over the total number of repetitions. That gives us the probability of L. How should we modify this so that we have the concept of conditional probability if it rains? Well, what we should do is, from all these repetitions in this experiment, we should only take the ones where it rains. So now in the denominator, we should only divide by the number of times it rains. And now, out of those, we want to see how many times the flight is late. So it's not the number of times that the flight is late, it's the number of times that the flight is late and it rains. Okay, and hopefully that makes sense as an intuitive definition of what we mean by conditional probability. And now what we can do to relate this to actual probabilities is to multiply and divide by the total number of repetitions in this experiment. Oh, and I didn't say this, but it's important to remind ourselves this experiment is just an abstraction, right? Like maybe we're modeling a flight that arrives tomorrow. It will arrive once. We're not going to repeat it over and over and over, but this abstraction is super useful because it allows us to have an intuitive grasp of what a probability means and reason about uncertainty in a quantitative way. Okay, so we've arrived here. Now we have that intuitively the conditional probability of L given R should be equal to this. And we realize something very interesting. We realize that what is this probability intuitively? Well, according to our intuitive definition, it's the probability of L intersection R, right? Because out of all of these repetitions, we're looking at the fraction where the airplane is late and it rains. And what about this guy? Well, this guy, if you realize, is just 1 over the probability of R, because the probability of R is the fraction of times that it rains. So intuitively, this seems to be a reasonable definition for conditional probability. The probability of the intersection divided by the probability of the event that we're conditioning on. Let's apply this definition to our example. Okay, so now we want to compute the probability of the intersection divided by the probability of rain. We already have the probability of the intersection. To compute the probability of rain, we're going to use this trick that you can explain with the Venn diagram, where we're separating rain into its intersection with late, and this is an intersection with the complement of late. Okay, those are disjoint, so we can just add their probabilities. And when we plug in all these numbers, we get 3/4. So the conditional probability that the flight is late if it rains is much higher, which is actually makes sense in the real world, right? Okay, so it's much higher than L. Okay, so now that we have an intuitive understanding of what a conditional probability should equal to, and we think it should equal to the probability of the intersection divided by the probability of the event that you're conditioning on, let's take a look at probability spaces. Let's remind ourselves of the structure of a probability space. There's a separate video about this, but let's remind ourselves quickly. A probability space has a set called a sample space, which contains all the possible outcomes in the probability space. Then there's a collection of events. Events are sets of outcomes to which we assign probabilities. We only assign probabilities to some events, to some sets of outcomes, and that's what the collection tells us, which events we assign a probability to. And then we have a probability measure that tells us what is the probability of each of the events in the collection. Okay, so imagine that we have this probability space, and remember that this is a Venn diagram where the area of each of these shapes represents the probability. So here the area of this big square should equal to 1 because the sample space always needs to have probability 1. Okay, so we're interested in this event A, and someone tells us, or we gain this information, that we know the outcome is for sure going to be within the event A. So now the question is, how do we update the probability space? How should we update this probability space? And that means updating each of these elements. Okay, so first of all, what should be the new sample space? Since we know, maybe pause the video for a moment and think about it. All right, so if we know that the new outcomes are going to be in A for sure, then it makes sense to make A the new sample space. Okay, so here we go. A is going to be the new sample space. Now let's think about how we update the collection of events. For each event in the original probability space, in the original collection of the probability space, for each event B, how should we translate it to the new probability space? Well, if we're interested in B, we know that the outcomes that are outside of A are not going to happen in our new probability space. In our new probability space, we only have outcomes within A. So that means that we should probably represent B by its intersection with A, because those are the outcomes that can actually happen. All right? So there we go. We replace every event B. I have trouble with B's and V's because in Spanish we just pronounce them the same. We're going to replace B by its intersection with A. We're going to do that with all of the events in the collection. You can actually check that this is going to be a valid collection. I'm not going to do it here because it would take a while, but like you just check that the unions are also going to be in the collection, the complement is also going to be in the collection. We already know that there's a sample space in that collection, right? We're saying that the sample space is A. Okay, perfect. So we have a new sample space, we have a new collection of events. Now we just need a probability measure to assign probabilities to those events. But you might say, but wait a minute, the original probability measure already has to assign probabilities to the intersection of A and any event B in the collection just by the properties of collections and probability measures. And you're correct. This probability is actually well defined for any of those intersections. But can we use it directly? There's one catch. Maybe pause the video and try to think what the catch is. The catch is actually that these probabilities are too small in the following sense. The probability of the whole sample space is equal to the probability of, by this definition, the probability of A intersection A, which is the probability of A, which in general is not going to be equal to 1. So that violates this condition that the probability measure has to assign 1 to the whole sample space. So how do we adapt the probability measure so that this is the case and we still preserve the structure of the original probability space? Well, we can just multiply everything by 1 over probability of A, which means that we're blowing up this square. And if you realize, I did this without telling you. So originally, and maybe you were wondering about why did I do this, when we were saying, oh, you have your original probability space and then boom, you have your new one, I was actually blowing up A so that now it has area 1, and these are like the areas actually correspond to actual probabilities in the Venn diagram. So I already did this in a bit of a sneaky way. So that's what we do. We scale every probability of the intersection by 1 over probability of A, and this gives us a reasonable definition of the conditional probability of each of those events given A. And guess what? We have ended up with exactly the same definition for conditional probability that we derived from intuition. So hopefully by now you're quite convinced that this is a very reasonable definition for conditional probability, and that's the definition that we're actually imposing. Okay, we're going to define the conditional probability of B given A as the probability of the intersection divided by the probability of A. And it's important to realize that this is a new probability measure in a new probability space where A is the sample space. Okay, so in general, in probabilistic modeling, we often call probability of B the prior probability, because that's the probability of B before we gain additional information. And we call the conditional probability of B given A the posterior probability, because this is the probability after we have updated with the new information, which is that the outcome is in A. Okay, very good. A note on notation, because it's very cumbersome to write this intersection symbols all over the place, we often just replace them by a comma. Okay, so if you see probability of A, B, C, A, B, C, that means the probability of the intersection of A, B, and C. And the same when we condition. Okay, this means that we're conditioning on the intersection of those events. All right, again, just to alleviate notation. Okay, so now that we have defined conditional probability, we're ready to talk about these 3 very important results. The first one is actually pretty simple. Once you have defined conditional probability, this is the definition of conditional probability. We can just multiply by probability of A on both sides, and we get an expression for the probability of the intersection as the product of the probability of one of the events times the conditional probability of the other one, given that one. Okay, we can do this both ways. The probability of the intersection is also the probability of B times the probability of times the conditional probability of A given B. That was, like this is super simple. It just follows directly from conditional probability. Often we want to apply the chain rule to more events. So let's see how that works. Okay, now we have 3 events, A, B, and C. Let's start by grouping B and C. So considering this intersection as the intersection of A and this other event that is B intersection C, which you can call D if you want, if this makes it clearer that this is actually an event. If we just apply the chain rule for two events to this, we get that this is equal to the probability of A times the probability of B intersection C given A. So now let's see how we can further expand this expression. And for that, we're going to consider the conditional probability of C given the intersection of A and B. And again, if you have a little bit of trouble visualizing that this is just an event, you can replace this by E. And now if we apply the definition of conditional probability to C and E, this is the probability of C given E, right? It's the probability of the intersection up here divided by the probability of E. And now what we can do is we can multiply and divide by probability of A here, okay? So this is here what we're going to do is we're going to multiply by probability of A divide by probability of A. And if we do that and group things like this, on top we're going to get the probability of BC given A, and underneath we're going to get the probability of B given A, okay? We get exactly this. And now we have an expression for probability of B intersection C given A as the product of this guy and this guy. So we can plug this in here to get the following formula, which is that the probability of the intersection is equal to the probability of A, the probability of B given A, the probability of C given A and B. The way I usually visualize this is that you have a bunch of events in here and you can bring them out. By bring them out, I mean write their probabilities and then multiply it by the rest. But when you bring them out, you always have to condition on whatever has come out first. So here A comes out first, just probability of A. Then B comes out, so you have to write probability of B given A. And then C comes out, so it's probability of C given A and B. This is just the way I think about it. The order is completely arbitrary. We can just, interchange the labels here. There's nothing special about the order A, B, C. So we could have written, taken out C first, then A, but we have to condition on C, and then we could have taken out B, and you have to condition on A and C. And you can do this for many, many, many events. You can prove by induction that, that the same formula holds. So you have like an intersection of many, many events. You take one out, you take one out, then you take another one out and you condition on whichever you have taken out before, and so on and so forth, okay? On and on. And you do this in probabilistic modeling many, many times. Something that I want to emphasize is that the order is arbitrary, but essentially because of conditional independence assumptions, we will see this later on, it's actually very important how you choose the order, both for homework problems, but also in real-life probabilistic modeling. All right, we can now move on to the law of total probability. Imagine that we have a sample space that is divided into a certain number of disjoint events. By that, I mean that every outcome is in one of these events, and they are disjoint. And now we are interested in the probability of another event B. When I see a B and I say event, I just want to say event. Anyways, we're interested in the probability of this event B, but we only have access to the conditional probabilities of B given these sub-events. And this is not so crazy, right? Imagine that we're modeling the flight being late and it raining. You might just have the conditional probabilities of what happens to the flight when it rains, what happens to the flight when it doesn't rain, and so on. So how do we combine all those probabilities? Well, we realize that we can cut up B into its intersections with these different events. And because they are disjoint, they should add up to give us the probability of B. And now, by the chain rule, we can just expand these guys into the probability of AI times the probability of B given AI. And that is essentially the law of total probability. So let's define it a little bit more formally. These events that I talked about that kind of cut up the sample space, so they're disjoint, but their union is equal to the sample space, that's called a partition in set theory. Okay, so a partition of the sample space is a group of events which are all disjoint, and their union is equal to the whole sample space. So if we have a partition and we want to express the probability of a set in terms of that partition, well, it turns out that we can again express that set as a union of its intersections with the partition, with each of the events in the partition. And now these guys are disjoint because the original events are disjoint. That's very easy to prove. You can do it on your own. And, okay, so this is why, okay, at the end, there is a typo here. I don't want to stop the video and start from the beginning. We will fix the typo right at the end. So, okay, so we have this as the sum of these probabilities. And now we expand them through the chain rule and we get the way of combining these conditional probabilities to give us the probability of S. Okay, so what is the typo here? The typo here is, for some reason, I put this sum there, which makes no sense, right? Because this is the probability of the union of those guys. There shouldn't be any sum. And then we see that these guys are disjoint, so that's why we get a sum of the individual probabilities, like in our picture. Okay, but this is the law of total probability. As you see, it just follows from basic properties of probability and then the chain rule. And in fact, I usually don't just apply it like this. I just usually rederive it for each example. But you can definitely apply it if you want. Okay, so let's apply it. Imagine that we have exactly the situation that I told you about. We know the probability that a flight is late if it rains and if it does not rain. As long as we know the probability of it raining or not, which is our partition, right? So maybe I'll draw a little picture here to connect it to our example. So we have a sample space like that. And what we're saying is that here it rains and here it does not rain. This is not a great picture because this should have an area which is 1/5 of the whole square, but bear with me, I'm not a very good artist. And now we're interested in the probability of the flight being late. So we carve it out between these two small events. Okay, and this is what I mean by the fact that I typically just rederive this because it's more intuitive to me. We want the probability of late. So what do? We take the intersection with L. Sorry, we want the probability of late. We take the intersection with R and the intersection with R complement, and then we expand using the chain rule. And that's the law of total probability, but again, it's just easy to just rederive every time. And then we plug in the probabilities. So this is 0.2, this is 0.75. What is that? Think about it for a moment. It's 1 minus 0.2, right? 0.8, and this is 0.125. Put that all together, boom, 0.25. I strongly recommend that for this type of examples, you pause the video at the beginning and you just do it on your own and then check whether you got it right or not. But obviously, we're all adults here, so do whatever you want. Okay, something very important before we introduce our third important result, which is Bayes' rule. Something very important to remember is that the conditional probability of A given B is in general different to the conditional probability of B given A. An example that I like to give is, imagine that A is owning a basketball and B is playing in the NBA. The probability that you own a basketball if you play in the NBA is probably 1. Like these people, probably all of them have basketballs. The probability of playing in the NBA if you own a basketball is extremely low. In fact, I own a basketball and here I am. So why is that? Well, if you go to the definition, the probability of A given B is equal to the probability of the intersection divided by the probability of B. And the probability of B given A is the same, but we divide by the probability of A. So in our example where A is owning a basketball, I think, right, and B is playing in the NBA, when we look at this conditional probability, owning a basketball if you play in the NBA, because this guy is very small, this guy is very big, okay? And vice versa, right? Here playing in the NBA, that probability is, sorry, no, the other way around. I said that exactly the opposite that it should be, okay? So let's make this very clear. A is playing in the NBA, right? No, sorry, A is owning a basketball. B is playing in the NBA. B is very small, so this whole probability is very big. Now I don't know anymore if I said it right or not, but this time it was right. And now here, the probability of A, which is owning a basketball, is pretty large, so the whole conditional probability is very small. I have actually a picture that will make this much clearer. Here we have a Venn diagram. We have the whole sample space, and we have these two events A and B. Okay, and A, which is owning a basketball, for example, is much bigger, it has more area than B. So what happens when we condition? First, we condition on A. We blow up A so that it has area 1, and this blows up the conditional probability by 1 over probability of A. Okay, and the area of this guy is the conditional probability. Now what happens if we condition on B? We blow up the small circle now, and we blow up by much more, right? Because this probability is so small. We multiply by 1 over that probability, which is small. Again, you can think of it as the probability of playing in the NBA, although here we're not going to get a conditional probability equal to 1. And now what happens is that the conditional probability is much larger because it was multiplied by this factor. Okay, so in general, the conditional probability of A given B is different to the conditional probability of B given A, but you can actually find one from the other as long as you take into account these prior probabilities. And that's called Bayes' rule. Okay, so Bayes' rule tells us that the probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of B. So we're correcting for these factors. This is another example where I usually just rederive this from the basic properties when I do problems, but up to you. You can just apply it directly. So let's take a look at an example. Imagine that for some reason, you have these probabilities that the flight is late if it rains and it does not rain, and for some reason you don't know if it rained or not, but you know that the flight was late. So you decide to say, okay, what's the probability that it actually rained? Okay, so how can we do this? Again, you can just apply Bayes' rule, and that's it, and that's completely fine. But let's rederive from first principles. The conditional probability of R given L is equal to the probability of the intersection divided by the probability of L. Okay, and now this guy, we get it from the chain rule, and this guy we can just get it from either the law of total probability, just apply it, or you can realize that you can separate it into late intersection R and late intersection complement of R, okay? Which is essentially the law of total probability. A pet peeve of mine is to just rederive these things as I go along. You don't have to. Okay, and now these guys, we can again expand them by the chain rule, and we get this expression, which is just Bayes' rule. So now we plug in all this information. Again, I recommend that you do this on your own and check the numbers, and maybe sometimes I will have made a mistake and you can laugh at me. The probability of that it rained if the flight was late is 0.6. Okay, which is not immediately obvious when you look at the other probabilities. Bayes' rule allows you to combine all of this information in a sound way. Okay, so what have we learned? We have learned an intuitive definition of probability in two different ways. We looked at it just from intuition alone, and then looking at probability spaces and how we should kind of blow up an event and so on. And we ended up with exactly the same definition of conditional probability. So now we're going to impose that as the definition of conditional probability. And then we looked over three fundamental results, which essentially just follow from the properties of probability and conditional probability. Those are the chain rule, the law of total probability, and Bayes' rule. And that's all I got. Thank you very much.